Hello, everyone. Welcome to our 8th edition of our developer community meeting. Today, I'm joined by Athanasios here, who will be providing a lecture on optimizing single core performance in CSL. So without much further ado, Athanasios, go ahead and kick it off.
Hello, everyone. Welcome to our webinar. My name is Athanasios, or Thanasis, as they said. You can call me Thanasis. And I'm very excited to talk to you today about the Cerebras software language, or CSL, which is what I've been working on as a compiler engineer for the past 2.5 years almost, since the very beginning of CSL. CSL is part of the Cerebras SDK, and at the end of the talk, I'll tell you how you can reach out to us and how you can get access, so you can use all that good stuff for yourself. Try them out for yourself. All right, let's get started. The wafer scale engine is the biggest chip ever built. It has 2.6 trillion transistors, 850,000 cores. It has the size of a dinner plate. You should see it up close, it's really cool. 40 gigabytes of memory and pretty insane memory and fabric bandwidth. Okay, so the question is, this is all great, but how can we actually use it? First things first, you can use the two most popular, some of the most popular machine learning frameworks like PyTorch or TensorFlow. But these frameworks are high level and they abstract away from the individual cores of the wafer. With CSL, you can really tap into the individual cores, and really the fabric now becomes a blank canvas for us, and we can let our imagination go wild, if you will. Okay, so far so good, but how can we actually use CSL? We can do that in 2 steps, actually 3 steps. Step number 0 is to specify what we call the layout block, as you see in that code snippet below. And within that layout block, we have step number 1, which is to specify a subset of RPs as a rectangle. We can use the whole fabric if we want to, all 850,000 cores. And then step number 2 is to specify the code that we want to execute on each individual PE, as you see in this loop there, where we specify the code in the tile code file to be the one executed by each of the P's within the rectangle that we outlined here. Notice that in the CSL language, we have these built-in or primitive functions that are prefixed with the @ sign. So you will see that many times today. So this is how we would specify where we want to execute our code and what code to execute in each individual PE. Obviously, this rectangle can be moved around the wafer, and this can be done with special compiler flags. But as far as the programmer writing the code is concerned, we just program for a specific rectangle. So this talk today, our talk today, is going to be focused on what's happening on that individual, on individual P's, in particular, how we can do single P compute, and how we can maximize the performance. And we can do that. One way we can do that we will explain today is to utilize a special capability of the wafer scale cores that is called data structure descriptors, or DSDs. And in this talk, I will explain what that is, how we can use it, and why we should use it, or when we should use it. Hopefully, by the end of the talk, you will have a good understanding of that. And also, I'm hoping you'll be excited to try this out for yourself. All right, let's dive in. When we talk about computation, one of the first things that comes to mind is loops. So here you see the syntax of a loop in CSL. This is a very simple one-dimensional loop from 0 to size -1. And within that loop, we are accessing a memory buffer A. It doesn't matter if we read or write. Here, a data structure descriptor, or DSD, is essentially a description of that access pattern for the memory buffer A. And we can create DSD values, as you see in this code snippet there, using the getDSD built-in. And let's see how we can call that built-in. So the first thing we need to specify is the type of the DSD. In this particular case, it's a 1D memory DSD, followed by an anonymous struct with fields representing the properties of our DSD. In this particular case, there's only one property, the tensor access property. Excuse me. But as you'll see later, we can have more properties when we create DSD values. So here we have the tensor access property that essentially describes the access of memory buffer A within that loop. You see that we specify the index of the loop, the length of the loop, and the access pattern for memory buffer A. Okay, so this is how we can create DSD values, but how can we use them? DSD values can be used as operands to special DSD operation built-ins, as we call them. And there are a few dozen of them. Just some examples here. Move 16 is just an assignment. We can add, we can perform floating point half precision multiplication, or multiply accumulate operation, single precision floating point add operation, and many more. But it's better if we actually look at an example. So I will now switch to my demo here. Hopefully this goes well. So let's actually see what a DSD looks like and how we can use it and why. This is the code that we compile for the individual PE. This is our layout block. As I showed earlier, we have one PE here, and we specify our code to be code.csl, which is right here. And this is our main task. This is the task that we are executing on that PE. Here you see the very simple one-dimensional loop that just writes a value to the memory buffer. And here you can see our DSD. We're creating the DSD value, and then the move operation here, we can use it as an operand to a move operation which is essentially the assignment. We assign 42 to every element of memory buffer A. So in a sense, this code here is equivalent to, semantically equivalent to the loop. Obviously, here we can, in the access pattern, we can define an offset, or we can have a stride like so, and so on. So if we try to execute this program, notice here that I'm measuring the time before, after the loop, and before and after the equivalent DSD version of that loop. So if I go ahead and run this, and hopefully that goes well, let's see. What we will notice is that the loop version is almost more than 34 times slower. So what you are seeing here is, by using these DSD things, we can replace loops. This is how you would typically write computation for wafer scale cores using DSDs. And this is one kind of a DSD. It's called the 1D memory DSD. Let's move to another example. What about nested loops? In this example here, we have a three-dimensional loop, and we have a computation in the body of the loop, an increment, in-place increment into memory buffer A, which is a three-dimensional tensor, and we read from another tensor. So here we can create two DSD values. This time, the type of the DSD is so-called memory mem4D DSD. It's called 4D because we can use up to 4 dimensions. In this case, it's just 3 dimensions. And here is our tensor axis. Notice here that the tensor doesn't really have to be 3D. Maybe that could be confusing here. So we can do something like this in a 2-dimensional tensor, or we can even do something like this in a 1-dimensional tensor. So the DSD really describes the loop structure and is associated with a single memory buffer and how we're accessing that buffer within that loop structure. So in this example, we have created our two DSD values to represent buffer A and B. And in this case, our buffers contain half precision floating point numbers, and we perform an add, just like in the loop. Okay, so if we run that example, we will see again that a similar speed up of it's over 30 times faster. So what we've seen so far is that we can create DSD values that can be of two kinds, 1-dimensional memory or up to 4-dimensional memory DSDs. We can use them as operands to special built-ins. There is a collection of them. I would point you to our documentation for the full list. And basically, this is the style that you would use typically when you program single wafer scale cores, where you would avoid writing explicit loops, but rather use this special capability, which is these DSDs, memory DSDs. Maybe I'll pause here to see if there are any questions so far. If there aren't any, I will keep going. In one of our previous webinars, the one presented by Andy Gill, we saw how we can route data across the fabric, also called, these are called wavelets. So how we can route wavelets across the fabric using the set color config built-in. The term color here, you can think of it as communication ports. So you will see that term many times in CSL, but you can think of it as communication ports. So we can set up these communication ports to let wavelets data flow through the fabric. In this talk, I will explain how we can actually receive those wavelets, use them for computation, and then also send results back to the network, again using DSDs to describe that process. Before I go into that though, on the left you see a diagram depicting how a processing element or a core looks like. So within the core, there is a router that we can configure using the set color config built-ins, and this router will forward data in receive and send data across the 4 cardinal directions, and also it can send data to the compute element, the core, where the actual compute takes place, and it can receive data from the compute element. So today I will explain to you how we can receive those data, how we can use them, and then how we can send them back to the router. Okay, so let's actually have a look at an example. Here we defined what we call a fab-in DSD, or a fabric input DSD, if you will. And here is our anonymous struct. This time it has 2 properties. The first one, called extent, represents the number of wavelets that we are expecting to receive. And then the fabric color specifies the communication port from which we are expecting to receive the data. And then below that, you see a fab out DSD or fabric output DSD with similar properties. We have an extent, which is the number of wavelets we want to send, and a communication port or a color in which we want to send the data to. And our main task here performs an addition. It receives data in the input color through the input fabric DSD, adds 42 to every element, every wavelet it receives, and then forwards the result back to the output. So if we try to run this example, there is no timing this time, just the computation to demonstrate that if we send in this tensor, we will receive back a result like so. So this is how we can use the flowing streams of data to do our compute, receive them, use the individual wavelets, and then send them back to the network. There is a problem with this though, because this operation here is blocking. So our compute is not going to proceed until all the data are received and all the data are sent out. And this is not great because obviously it's going to be, well, obviously it's going to block the progress on this PE because we don't really know when the data are going to arrive. Maybe the data are not ready yet for a compute element to receive them, or the network might be congested. There could be a traffic jam, and which would not allow the CE to send the data out. So to solve this problem, I'll show you another example of how we can actually solve this problem. Our input DSD here now has a third property. So it's the same extent, which is 100 elements. So we are receiving 100 elements in this case. This is our input port. Now there is an extra property, which is an input queue. This is a small built-in FIFO queue that allows us to buffer data as they come in and allows us to perform operations or computation on these DSDs asynchronously. So we can let these small FIFO queues operate in the background, and we can keep going with our own computation. So here is an example of how we can use that in a main task. We use our input DSD and our output DSD. This time, both of them specify an input queue in this case and an output queue. There is a limited number of queues depending on the hardware generation. And the operation is marked as asynchronous. And here I added some compute just to show you, to demonstrate the difference between the asynchronous version and the blocking version. Here, our PE wants to move on with the computation. Maybe we want to do some compute, then send data again. In this case, I just want to demonstrate that simple compute performance. So first, I will remove this async, and I'm going to remove the input queues and the output queue, the FIFO queues. And this is the same version as we saw earlier, which makes this operation blocking. So if we try to execute that version, and then we will add back the asynchronous property and see the dramatic difference in performance. So here, this took almost 8,000 cycles to complete. And if we add back our output queue, input queue, and the asynchronous property, this will allow the compute to proceed immediately, and the queues can operate in the background, and we don't have to worry about it. So if we try that again, hopefully that works. You see that being significantly faster because, as I said earlier, it allows us to proceed immediately with our compute. So what we've seen so far, we've seen two classes of DSDs, memory DSDs that allows us to perform compute much faster than explicit loop nests. And we've seen fabric DSDs that allows us to access the data flowing through the fabric and use them for computation, send the results out, and also how to do that asynchronously. Again, I'm going to pause here to see if there are any questions so far.
Hi, Thanasis. Sorry to interrupt. So in your example, the input queue and output queue in the DSDs is same, right?
You're referring to this example?
Yes.
Mm-hmm.
What if I make it different?
Yeah, they can be different.
Yeah, because previous I had a bug because of this input queue and output queue sometimes cause some problem if I make it same, because it has some restriction, the maximum that I can use, like for example, how many DSTs maximum I can use the same input queue?
Yeah, there are some limitations because these correspond to hardware resources, so they are inherently limited. So the user needs to be aware of these restrictions. As you pointed out, in a later example that I will show you, you will see how we can actually lift some of those restrictions with a different kind of a DSD that maybe you are familiar with it already. But
okay, thank you so much. Thank you.
Yeah, no problem. And please feel free to reach out to our forum if you have any specific questions that we can help you with specific your specific example as well.
Yes, sure.
And oops, any other questions so far? Okay, so moving forward with another cool use case. As I explained earlier, DSDs can be used as operands to a specific list of operations. What happens if the operation we want to perform is not in that list? That's okay. We can use this built-in called map to use DSDs for arbitrary compute. And I'll show you an example of how we can do that. Here is our main task, and here we're using the map built-in, and we have DSD operands passed into that built-in, and I'll explain step by step what's going on here. First, let's look at our DSDA value. This is a memory 1D DSD. And notice how the tensor here is two-dimensional, and basically here we are extracting the diagonal of that tensor. And what we want to do here is we want to compute the square root, half precision square root, which comes from our standard math library imported here. The square root, obviously, it's not part of our built-in operations on DSDs, so we can use our math library for that. And we would compute the square root of each element of the diagonal of tensor A and send the result out to this fabric out DSD, and the extent here is 5, so just 5 elements, sending out to this output caller. Here is another example where I have written a function with some random compute that I came up with. Doesn't really mean anything, just some arbitrary computation here. And the first argument to the map built-in is the callback function that we want to call. And then this is followed by one argument for every input parameter of our function. If the parameter is a DSD, and here we can mix and match any DSD, here we have a memory and fabric input DSD, we can mix scalar arguments, and so on. Here, the first argument is a DSD, and therefore this parameter here corresponds to an individual element of that DSD. So remember, DSDA is the diagonal of buffer A. So for every element along the diagonal, we call this function, and this is its diagonal element, followed by the two coefficient arguments, 2 and 6, followed by another parameter that basically comes in from the fabric through a fabric input DSD, and the result is written back in place to DSDA. We can also do a reduction. In this case, we basically sum all the elements of DSD B into this sum variable, this global variable here. So now I want to show you another kind of DSD called FIFO DSD. And I'll walk you through an example because it's better to understand this through an example. Let's assume that we have two PEs communicating with each other, one PE sending data to another PE, as you see here. What if the receiver PE has some heavy computation, and which means that it's going to take a while until the receiver PE will be able to actually receive the data sent by the sender. Earlier, I showed you how we can use these built-in FIFO queues to communicate data asynchronously, but these queues have limited size, and if the receiver is busy for a long time, these queues are going to be overwhelmed. So how can we solve this problem? What we can do is we can place a PE in the middle. That is one way we can use FIFO DSDs. There are many different variations, but here I want to show you the simple case to demonstrate how FIFOs what are FIFO DSDs and how to use them.
Hey, Athanasios.
Yes.
We have a question in the chat. Computation using the map built-in is faster than that of using the iterator, right?
Yes, absolutely. Yes. Again, it's faster than using explicit loops. Yes, for sure. The same order of magnitude speed up. So with FIFOs here, we can use the entire memory of the FIFO P in the middle to buffer elements and fully overlap communication and computation. So FIFOs can act as arbitrary sized buffers that can absorb bursts in either receiving or sending directions. So let me show you an example of that. First, okay, I seem to be offline here. So my examples are officially not working. I apologize for that. But basically, the example I was hoping to show you would demonstrate how the previous example, where we used asynchronous communication, can actually block the sender until the receiver completes its computation. So that can snowball and create back pressure, crippling more PEs in the process. And by using that FIFO PE in the middle, we can receive data as soon as they are available, and then send data out as soon as they are requested. So we can effectively overlap communication and computation. All right, so what we've seen so far with FIFOs is that we can use FIFO DSDs to, when the small input and output data queues are not big enough to absorb our traffic. And with FIFOs, we can use arbitrary big queues instead to absorb bursts of traffic from either direction, receiving and sending. And that allows us to overlap computation and communication, and prevents PEs from being blocked when the network is congested or data are not ready to be received, and so on.
One more question for you.
Mm-hmm.
The second PE is used as a FIFO and cannot be used for computation. So there's a trade-off there, correct?
Absolutely. So this is just a demonstrative example, or probably oversimplified, but the FIFO can be part of the receiver, can be part of the sender. You can have compute in your FIFO PE as well. Also, you can, as I said, you can use the entire memory of the PE for the FIFO, and you can use multiple PEs for the FIFO. If you want even more memory, you can use multiple PEs to accumulate all the memory, depending on your use case. Yeah, so does that answer the question?
Yes, thank you for your answer.
Cool. Yeah, it's really unfortunate that my connection here failed. I was really looking forward to show you that example.
Is it possible that you can share your example, maybe on GitHub or somewhere?
Oh, yeah, absolutely. And in the example, I was showing how we can play around with the parameter of the FIFO size. We can make the FIFO bigger or smaller, and depending on the size of the data we are moving around and the size of the FIFO, we can see the time measured in the sender going up or down by playing around with these parameters. All right, I think that's all I had so far. And just so you know, we are on the verge of our new release for the SDK. That's the 0.6.0 release with some new features in CSL, including a new collective communications library that consists of broadcast, scatter, gather, and reduce primitive operations. We also have synchronous FIFO capabilities now. The example I showed you earlier, the FIFO can really work automatically in the background and you don't have to worry about it. But sometimes you want to say, write 10 elements in the FIFO, specific number of elements, or read specific number of elements from the FIFO. There are some use cases there. And the FIFO can be full or empty, in which case there are some exceptions that are thrown, and we can also provide the ability to activate a task when the FIFO becomes has elements to pop from, or it's not full anymore, so we can push more elements to it. So we can get notified when that happens. Also, we are developing an RPC-like mechanism where we can, where users can interact with the device from the host. And we have introduced some built-ins that allow us to advertise data resident on the device so we can interact with them. In the previous release, we introduced generics, sort of like templates, where you can write functions for any type arguments. And we have updated our standard library to work with the generics. So you can call our standard library API with passing data of any type. And we also have a cool new feature where you can import data from JSON. So that's all part of our new SDK release. This is how you can get access to our SDK. Uday, would you like to say more about how people can reach out to us to get access?
Absolutely. Yeah, for those who are interested in downloading and using our SDK, if you can go to the previous slide, Thanasis. We have a QR code up here that you can scan. Alternatively, if you want to go to our website, cerebras.net, and under developers, request access to our SDK, that'll navigate you to the same place. Simple form and a chat with a couple of our team members and an NDA, and we'll have that SDK in your hands. So fairly simple, but as we normally mention as well, you won't be without support. When you do have access to the SDK, you'll also have access to our discourse site, where our team is happy to answer questions and provide best practices support as you maneuver our CSL and our SDK.
So yeah, that's all from my end. Uday, back to you.
Yeah, no, thank you so much for this presentation. I will do one last check just to make sure that all questions have been answered. If anyone does have a question, yeah, feel free to ask right now.
Very unclear in terms of what students are getting.
Sorry to interrupt again. Thanasis, I just wonder when are you going to release the SDK 0.6, and I also wonder, can you also going to share some benchmark program example with the new release, like SPMM or SPMV?
I don't think there is a fixed date yet, as far as I understand, but it should be very, very soon. And the second part of your question was, can you repeat that?
I mean, previously you provided some like stencil computation kind of good program. I just wondered, within the new release, are you going to provide like sparse matrix multiplication or sparse matrix vector multiplication CSL example or benchmark program? I just wondered.
Yeah, there are some new benchmarks in the release. I don't remember the specific ones off the top of my head now, but yeah. I'm not sure specifically. You mentioned sparse matrix multiplication. I'm not sure this one is part of it.
I see. Or the gem example? Yeah, because this tool is mainly related to my research. I try to implement myself, but I'm so suspect
cool.
it's optimization kind of stuff. I wonder if you, I don't know if you provide some example or if you're going to provide some benchmarking within maybe features, but soon features, near features.
Yeah, if it's not part of this release, we can definitely try to include it in the next one. Sounds like a great example to include. Yeah.
Another thing is, I'm sorry, I feel like I'm dominating, but I have another question. I'm sorry about it. At the beginning, you mentioned PyTorch and TensorFlow. As far as I know, previously you were not supporting the implementing kernel and just call this kernel from the PyTorch or TensorFlow level. So I wonder if there is any update regarding this. If I could like to complete or implement some, let's say, convolution kernel on the CSL. Can I call this kernel on the PyTorch or TensorFlow?
I don't think I can answer that question. I'm not as familiar with the PyTorch and TensorFlow products, but that's a good question. Hopefully, we will maybe sometime in the future be able to do that. Yeah, I'm not as familiar with those products myself.
Thank you.
Mm-hmm.
Athanasios, it looks like there's a question for you in the chat. There might be a limitation of FIFO depth since the FIFO is a hardware resource. What happens when the two directions share the PE? FIFO depth would become half?
There might be a limitation of FIFO depth. So the FIFO DSD can use the entire memory of the PE. So there is a limitation, which is the memory of the PE. So that is correct, since the FIFO is a hardware resource. Yes, so the two directions are going to share the capacity of the FIFO. You're right. The FIFO depth is so there's one FIFO that is shared asynchronously. FIFO is sort of like implemented as a circular buffer, if you will. So it's going to flow through the memory as things come in and out. So in that sense, you can think of it as one chunk of memory, and the read and write operations are just asynchronously reading and writing from that memory. And obviously the PE is smart enough to handle all the details for us.
Okay, thank you for your answer. And one additional question. So, as far as I know, the PE has 8 banked shared memory, right? So it also means that 8 direction can run asynchronously if one PE is used by 8 directions, 8 colors, 8 FIFO, or right?
I see. So your question is whether we can use the FIFO asynchronously for multiple directions. Is that your question?
Yes, and it's up to 8 because there are only 8 bank in shared memory, and not shared memory, SRAM.
That's a good question. I don't think that is possible. I think its FIFO is is associated with one port, input and output port. Obviously, you can declare multiple FIFOs, but you really don't want, because this is asynchronous, you really don't want these multiple reads or multiple writes happening at the same time. So you can have the read and write happening asynchronously, because different communication channels correspond to different data. So it is possible in theory, but you really need to be careful to not mix your data into the same buffer. So it's really kind of risky. Nothing will prevent you from doing that, but it's going to be risky to orchestrate the data.
Okay, so let me confirm that you mean that output Q, so there is a number assigned for the input Q, and we can mix up, we can use the same input Q number for different DSD, but your recommendation is not to do that, right?
Yeah. I think so, if I understood your question. Yeah.
Okay. Okay, thank you for great answers. Yeah, that's all.
Awesome. Any other questions before we wrap up? All right, Athanasios, thank you so much for your time. Thank you everyone for attending and asking great questions. And yeah, we look forward to presenting more interesting topics in 2023. Thank you all.